I welcome all of you to this inaugural mini course series. The Indian Women and Mathematics IWM has been organizing various activities throughout the year and past many years. Mini courses are one of the mini courses are one of their many initiatives. Previous mini courses on an online format were delivered by Professor Limaye, Professor Karandikar, Professor Bakshi, and Professor Neela Natraj. Today we have privilege of hosting a distinguished mathematician, Professor Ram Murty. He will share his invaluable insight and expertise with us. He will talk to us on how to do research in mathematics. Before we begin the main talk, I would like to invite Professor Riddhi Shah to say a few words about IWM initiative and its activities.
Good afternoon, everyone. Good morning to Professor Ram Murty. Indian Women and Mathematics is a collective of mathematicians. It's in existence since 2009. The first activity happened in form of a conference at JNU. The aim of our activities is to promote mathematics research and teaching amongst women in India. We have annual conference every year and also regional workshops which are held over a weekend in different parts of India. And we also have winter schools which are meant for undergraduate students. And visitors program aim is designed in such a way that 3 distinguished women mathematicians every year go to different parts of country, especially non-metro town, and deliver non-technical semi-popular talks to encourage women to and young girl students to take up a career in mathematics. Our annual courses and our mini courses, which are online, aims to reach is not just to people in India, but all over abroad. And we are funded by National Board for Higher Mathematics, Department of Atomic Energy, Government of India. And we are also supported by Committee for Women in Mathematics, International Mathematical Union. And I welcome you all. And it's an honor to have Professor Ram Murty tell us about the art and science of research. We all look forward to it. Thank you.
Thank you, Riddhi. Now I request Professor Abhay Soman to introduce Professor Ramurthy and chair the talk. Without further ado, I hand over the stage to him.
Thank you, Archana. It is my immense pleasure to introduce Professor M. Ramurthy. He is currently the A.V. Douglas Distinguished University Professor and Queen's Research Chair at Queen's University, Canada. His research focuses on number theory and related areas, with a particular interest in the theory of zeta and L functions, Artin's conjecture, automorphic and modular forms, Siev's methods, Selberg's conjectures, and Lagrange's program. His research work encompasses wide topics and has influenced almost every topic related to the number theory. He has published several influential papers in reputed journals. He has guided more than 50 PhD and master theses and has mentored more than 39 postdoctoral fellows. Furthermore, he has authored several books and monographs. For instance, his problem book trilogy, Problems in Algebraic Number Theory, Problems in Analytic Number Theory, and Problems in the Theory of Modular Forms are now standard references. These books are known for their student-friendly way of problem-based approach to the learning. His monograph, Non-Vanishing of L Functions with Professor V. Kumar Murty, was awarded Balagar Prize for their significant contributions to the theory and for bringing together results on non-vanishing of L functions and mathematical problems arising in different contexts. He has received several honors for his outstanding contributions to the mathematical exposition and research. He has been adjunct professor at various reputed institutions across the globe. He He is a recipient of Coxeter James Prize, Jeffrey Williams Prize, Queen's Research Prize. He was awarded an Excellence in the Graduate Supervision in 2018, and this year he has also received the CRM Fields PIMS Prize. He is an elected Fellow of the Royal Society Canada, Fields Institute, National Academy of Sciences, Indian National Science Academy, and American Mathematical Society, to name a few. Apart from mathematics, he is also interested in Indian philosophy. He has been cross-appointed to the Department of Philosophy at Queen's University, where he regularly gives lectures on mathematical logic and Indian philosophy. In 2013, he published an introductory book on the Indian philosophy. Now we shortly start the mini course, but before that, we have a few requests to participants. We kindly request everyone to maintain dignity and decorum throughout the mini course. Please refrain from posting anything unrelated to the lecture. If you have any questions, please post them in the chat box or raise the hand to ask the questions during Q&A session at the end of the lecture. So without further ado, we invite Professor M. Ram Murty to begin this mini course on how to do research in mathematics. Over to you.
Well, thank you. Thank you very much. Thank you, everyone, for inviting me to speak to you today. I want to share with you some, I would say, nuggets of wisdom that I had acquired over the course of life that may help you in doing your own research work. So let me make a disclaimer first. This talk is certainly not any recipe on how to do research. If there was such a recipe, then we can program computers to do research, and at the moment, this is not the case. Even ChatGPT cannot seem to prove new theorems. So even with that disclaimer out of the way, I just want to discuss general principles that one can apply irrespective of any field. So what I'm going to say might be illustrated through mathematics and in some sense number theory, but in general, they can be applied to any field of research. So I'll try to outline these principles, give illustrations from science generally, and more specifically from mathematics. And the basic tools are the mind and the mind's movement in time, called life. So, the purpose of life. Let me start with this philosophical question. According to the Taittiriya Upanishad, life is meant for only two things: study and teaching. Swadhyaya pravachanabhyam na pramaditavyam. That's the verse. Do not refrain from study and teaching. The human being is an organism that is ideal for this purpose. In other words, life is actually meant for education and self-education. A great sage once expressed this very beautifully: as long as I live, so long do I learn. And so this is the reason that human beings have been endowed with this marvelous instrument called the mind. The mind is the instrument we're going to use in doing research. So all of us are where we are today because of our mental development. And so whatever we want to study, the tool is the mind. So you have no other choice but to use this tool. So in the study of mathematics is different from the study of anything else, such as other sciences like physics, chemistry, biology, or subjects like the arts, literature, history, or social sciences. Mathematics seems to be both an art and a science, and no other subject seems to enjoy the status. So the study of mathematics requires a mind that is not only scientific, but also artistic. In one of the Upanishads, I believe, it is stated rather boldly that mathematics is at the head of all the sciences, like the crest of the peacock. In fact, the verse describes the beauty of the crest of the peacock, which if you analyze it very carefully, you will see it's a very delicate piece of artwork, and the poet describes mathematics as being in a similar beautiful way. So we not only want to prove theorems, but we want beautiful theorems. and beautiful proofs, so whatever that may mean. So there's this kind of aesthetic dimension to the doing of mathematics. We all know that beauty lies in the eyes of the beholder. So part of education is learning to see beauty. So this is, if you want to do research in mathematics, you have to learn first to see beauty in mathematics. So the artistic side of research, mental development needed to do mathematics is different from the mental development needed for the pursuit of other branches of learning. On the one hand, we need to have a high order of logical thinking, which is essential in all of sciences. And I think everyone understands the importance of logical reasoning. But on the other hand, we need to have a high order of a sense of beauty or aesthetic delight. I don't think this can be taught. We can probably teach logical thinking through what we do now in courses in mathematics and other subjects. But this aesthetic dimension is something that you have to cultivate, just like the aesthetic dimension to appreciate music can only be acquired by listening to good music. So this is very important in the musical tradition, and mathematics is not that different. So this talk is about how to cultivate both of these qualities so that the graduate student research, whatever that word may mean, becomes a bit easier. So this is why I've called this particular talk the art and science of research. So what are the ABCs of research? So what are the essential qualities we need to bring into our mathematical study? There are three: attention, avadhanam in Sanskrit, avadhanam, beauty, anandam in Sanskrit, and classification, adhyayanam in Sanskrit. So these are three words that are there in the Upanishads, and they're emphasized again and again. Many probably already know these three words, but these are the three most important words that occur in the Upanishads: avadhanam, anandam, adhyayanam. These three qualities are not linearly organized, but they rather should be developed simultaneously. So the power of attention has to be cultivated, the appreciation of beauty, and the ability to classify, organize, essentially the idea behind what's called Sankhya Yoga in the Indian philosophical tradition. So regarding the third quality, the student must get into the habit of making notes or having a notebook to systematically cultivate these three qualities. I will speak a little bit more detail in the second half of this talk, when we will talk about the habits of research, that habits to be cultivated. But here now we'll just talk about what are the methods of doing research. So the preparation for discovery, the first step is to find some mathematical theorem that you find beautiful and remarkable. I think this is the most important thing. So where I'm basically addressing my talk to a student who has perhaps finished the basic undergraduate program and now wants to enter, let's say, graduate school to do a PhD. And the mindset that you had as an undergraduate is not the same mindset that you would have to be a graduate student. The most important thing the graduate student has to have is to appreciate beauty in mathematics. So there it is on the mathematical landscape, like a Himalayan peak, and you gaze at it in wonder and awe. So there's this remarkable theorem that it's like a mountain landscape, and you find it beautiful. So that is the first prerequisite for this. As you gaze at this beauty, attention, you begin to see a path on how to explore it further. And you discover the steps, classification, to climb upwards. And slowly, slowly, more and more nuances of understanding begin to emerge. So let's now discuss this science of research. Research essentially is about asking good questions. The ability to ask good questions is the essence of research. Method of questioning is the way to gain knowledge in all philosophical and scientific traditions. If you go back to the Indian philosophical tradition, it has always been, vitarka, questioning. Questioning has been a method of gaining gnana, as they say. But these can't be idle questions or idle speculations. They have to be precise. They have to have a singular goal of achieving greater understanding into the nature of things. And as this is a mental process, it requires energy and stamina that can only be described as churning of the mind. So at the beginning, I told you, the instrument you have to do research is the mind. Then the question is, if that's the instrument, I have to know how to use the mind. And this requires these three processes, the avadhanam, attention, energy, anandam, appreciation of beauty, dhanam, that the classification process that I mentioned. So all of these three require energy and stamina that can be called churning the mind. Now, in the Puranas, a beautiful story appears in our Puranas and talks about Samudramantam. So here is a little artist's picture. I'm sure many of you are already familiar with it. The story is that in the Vishnu Puranam, the Devas and the Asuras want Amrutam. Amrutam is actually code for knowledge. And they realize that they have to churn the ocean, but they have to join forces. So here you have the Devas on one side, the Asuras on the other side. Vasuki is the divine serpent that they use. Mount Meru is the mountain. And of course, the tortoise at the bottom is the Kurmavatara. Vishnu has to take the Kurmavatara in order to keep the whole thing stable. And they start churning. And when they start churning, first the toxic halahala appears. And Shiva has to rescue them by essentially drinking it. Of course, he holds it in his throat. He doesn't actually swallow it. And that's why Shiva has a blue throat. But after the Shiva rescues them, they have to continue the churning again. And this churning gives rise to all the jewels of knowledge. Kamadhenu appears, the goddess Saraswati appears, the god of medicine appears, and so on and so forth. All these wonderful things start appearing. So how to churn the mind is basically how to ask good questions. So Samudramantam story is actually very profound, very philosophical, very deep. I would urge you to meditate on that, the meaning of that story. And here's a much more modern version of the same picture. So I would like to present to you an eightfold method of asking good questions, or eight methods of churning the mind. This is the essence of knowledge, how to gain knowledge. And the answers may depend on how you identify yourself. So you see, it's an interesting thing. Remarkable amount of philosophical aspects are there, psychological aspects are there in the process of research. So here's an example. What is 2 + 2? Sounds like a simple question. The engineer can answer it by saying it's 3.999 because he uses a calculator, he or she. There's no gender attached to these professions. The physicist runs an experiment and finds that the answer is 3.8 and 4.2, somewhere between there. So each is approaching this question from their own mindset. And according to the mindset, you have a different answer each time. The mathematician says he doesn't know, but can show the answer exists. The philosopher, of course, asks for the meaning of the question. And the accountant asks, what would you like the answer to be? So you have these different approaches to the same question. This is a good joke, but it also tells you a very profound process aspect of the mind, which in our Indian philosophy, it is recorded in a very beautiful sutra, Yada Bhavam tada anubhavam. That means how your attitude, bhavam, feeling, attitude towards the question determines your experience. So if you think there's nothing there, well, there's nothing there. If you think there's nothing beautiful in this, well, there's nothing beautiful in this. But if you find it very beautiful, very enjoyable, you will find new things that emerge in your mind. So yada bhavam tada anubhavam is an essential aspect of research. It's there in the Maitri Upanishad, actually, if you have studied it. That's where this particular verse occurs. Now, let me begin with the most basic of methods of trying to do research, which I call the survey method. And survey method is open to everybody. Anybody can do it. It doesn't require too much preparation. It consists of two steps. First, you gather facts, and second, you organize them. And so arrangement of ideas leads to knowledge and understanding. So in the process of arranging the ideas, you also find out what is missing, and this is a big idea. I want to illustrate how the survey method can lead to a spectacular discovery in the annals of science. And the example I want to give you is the discovery of the periodic table in chemistry. All of you probably know about this, but anyway, let me just give it to you. The periodic table, here's Dmitry Mendeleev. He organized the existing knowledge of the chemical elements and was surprised to find a periodicity in their properties. Now, Dmitry Mendeleev, you might know, was no college professor. He was actually a high school teacher. And he was trying to teach his students chemistry. And in trying to simplify understanding, he thought, let me just organize these chemical elements according to their properties. And lo and behold, when he organized this knowledge, he found a profound connection about the atomic number and some sort of the atomic number, the periodicity of the atomic number, which is a number of atoms in the thing, allows you to gain knowledge of the whole of chemical elements. And many of you may know that he found missing elements. And I think over the next 50 years of chemistry, people were looking for these missing elements. And every time somebody discovered one of the elements that was predicted by Mendeleev, they got the Nobel Prize. This poor guy died in poverty, but all these other people who came afterwards gained the Nobel Prize just by discovering the elements that he had predicted exist. So in the process of trying to write a student text in chemistry, Mendeleev decided to gather all the facts and known about the elements and organize them according to atomic weight. I have heard many times people tell me from reputed institutes that your job is not to teach, your job is to do research. But I disagree with this. I think teaching and research have to go hand in hand. And here's a superb example of a person who was actually a teacher, and he was trying to simplify existing knowledge. And in the course of that, he finds a cosmos of new discoveries, a cosmos of new discoveries. So the periodic table now sits as the presiding deity in all chemistry laboratories around the world. So here they are. Each discovery of a missing element predicted by Mendeleev led to the award of the Nobel Prize in chemistry. You can actually write a whole book on this now, the discovery, all the elements, the discovery of the periodic table. So how did this begin? It's the survey method of research. Now I would like to move to another method of research, and I call this method the method of observations. And careful observations lead to the discovery of patterns, and patterns lead to the question, why? Opening the door for the underlying theory that explains the patterns. So, in fact, some people go as far as saying, what is knowledge? Knowledge is pattern recognition. What is intelligence? Intelligence is pattern recognition. So people now say, oh, ChatGPT can discover patterns. Yeah, it's stochastic method of pattern discovery. We can debate that but it certainly helps in discovering these patterns that you may have not seen before. An excellent example is the Michelson-Morley experiment that the speed of light is constant, independent of any relative motion of the observer. So in physics, in the 19th century, people had postulated the existence of what's called the ether, some sort of medium in which light travels. And so the question was, if light is traveling in this ether medium, if it is going with the grain, the speed would be faster, and if it's going against the grain, the speed would be slower. And so they tried to see whether this is true or not. And they devised experiments of movement of light, either with a stationary frame, like illustrated in this image, or in a moving frame. And they found that no, there was no evidence of the ether. The speed of light is constant no matter what. And now the question was, if the speed of light is constant no matter what, which was observed, it led to the question, how do you now view physics? You see, in the case of physics, there's always this vector addition of velocities. You add velocities, there's always a vector addition formula, so you can get, if you have some particle of light traveling at this particular thing and it is moving in a particular medium, which is also traveling, the speed of light relative to the stationary frame must be faster than the original speed of light at the stationary frame, but that is not the case. So all of physics came unraveled simply because of this careful observation. And so I think many of you know, physics had to be revised. You had to now take the constancy of the speed of light as an axiom. And so in order to do that and then redo physics again, not from the Newtonian perspective, but from a more relativistic perspective, what happens? You get the theory of relativity. So careful observations lead to asking questions, which is the essence of research, as I mentioned at the very beginning. And in this particular example that I'm using to illustrate, we have the theory of relativity. So that's a big example of the method of observations. A third method of generating questions is the method of conjecture. The method of conjecture. So the Michelson-Morley experiment could not be explained by Newtonian physics, but this led to the conjecture that there must be a larger theory which will explain the observations. And Newtonian physics took space and time to be absolute and fixed. And from this standpoint, the Michelson-Morley experiment is a contradiction. So the startling axiom then is that space and time are not absolutes. And for those of you who know Indian philosophy, will know that in the ancient tradition, Shankara already said this, that space and time are not absolutes. In fact, space-time causation, Deshakala Nimitta, it's called in Sanskrit, Deshakala Nimitta, space-time and causation is Maya. The Indian theory of Maya is the space-time causation. And the idea that in order to get enlightenment, you have to transcend Maya is the Advaita Vedanta's central thesis. And it all, we knew this in some sense, I mean, not from a physics perspective, but from a philosophical perspective, that space and time and causation are not absolutes. So they seem to conspire to ensure constancy of the speed of light, whether the observer is in a moving frame or a stationary frame. And we will try to return to this a little later on to illustrate some other aspects of our thing. So this method of conjecture is a very important method. You observe a particular pattern, and the pattern leads for you to make a hypothesis, a particular conjecture that will then lead to knowledge. So in mathematics, we have the famous example of Ramanujan conjectures. In 1916, Ramanujan was studying the coefficients of a certain infinite product, he observed some remarkable properties. And this product is given rather innocuously by this formula. Product Q times 1 minus Q to the n to the power 24. You expand it as a power series in Q, and then you find these coefficients tau of n. And Ramanujan thought these numbers are very important. And so he made computations so extensively. Actually, I wrote down 30, but I think Ramanujan wrote down the first 100 numbers. And surprisingly, he noticed patterns in these numbers. These numbers, as you can see, are growing in absolute value very fast. And Ramanujan made some conjectures. He noticed that tau of mn is tau of m times tau of n whenever m and n are co-prime. Then he noticed that tau satisfied as a certain recurrence relation for prime powers. And then the third thing that he noticed was that tau of p was always less than 2 times p to the 11 halves. He couldn't prove any of these things, but it's a big deal that he made these conjectures, because that is essentially what inspired 20th century mathematics. It also inspired what's called Hecke theory of modular forms. It also inspired what's called the Langlands program. So these conjectures led to the development of the theory of modular forms and the theory of automorphic forms. These are a big deal in 20th century mathematics. So let me now move to a fourth method of generating questions. And this fourth method is what I call reinterpretation. So the method of research examines traditional concepts and tries to look at them in a new light. In some sense, the example that I had just given to you in the context of Newtonian physics versus Einsteinian physics is a case of reinterpretation. You had to reinterpret the understanding of space and time. And of course, causation. It's usually not said in physics, but you have to reinterpret the whole thing. What is causation? That's a very, not only great philosophical question, it's also a great question of mathematical physics. So such a method does not negate past understanding, but expands it and sees it as a special case of a larger phenomenon. So the Michelson-Morley experiment forced physicists to re-examine Newtonian physics and to question its fundamental axioms. And first and foremost were our notions of space and time. The special theory of relativity, which all of you know, postulates that time dilates and space contracts in order to make sure the speed of light is always constant, irrespective of the frame of observation. His theory reinterprets space and time. They're not absolutes, nor are they independent. They are interdependent. And now we speak of what's called space-time. But of course, space-time and causation, physics, I don't know why it doesn't put this causation part into the picture. Deshakala nimitta is what is the word that Shankaracharya had used for space-time causation. And Deshakala nimitta is essentially, you've all heard of Maya, Mahamaya, the grand illusion, as it's called in the Puranas, but that's really space-time causation. Gravity in Einsteinian physics is seen as a curvature of space-time. So Einstein's theory led to a new view of gravity, not as a force that pulls things down, but as a curvature of space. For example, why does a body revolve around the sun, let's say? It's because the space around the sun has been bent, curved, and the planets then move in these grooves that are created by the bending of space and time. And this particular view of space and time was a big deal in the 1930s in physics. They had noticed that light actually bends due to the force of gravity. They didn't know this before. If light is traveling on the surface of a four-dimensional spheroid of sorts, and gravity is really the bending of space, then around the sun, which is a very massive object, space would be distorted, and therefore light would have to bend. And this experiment, this view of space and time from Einstein's theory predicted that light would have to bend, and this was tested in the 1930s. And it led to Subramanian Chandrasekhar postulating the existence of black holes. The birth and death of stars in 1938, Subramanian Chandrasekhar showed that this view of gravity, that bending of space, allows for the existence of black holes. So if a massive star dies, the space around this massive star bends, and as if no light will escape from that thing. And that bending of space around such a massive star leads to the existence of black holes. Chandrasekhar predicted it in the 1930s, actually, and exactly for this reason. But only in the 1980s was it tested in an experiment by another physicist by the name of Fowler. And I think Fowler and Chandrasekhar both got the Nobel Prize in 1980s. Now, let me give another example of reinterpretation from a more mathematical perspective, unique factorization. Here's a little cartoon. Research institute, you always think of a research institute as essentially answering unanswered questions, but the research institute also will look at unquestioned answers. I suppose, many religions have answers for basic questions, and maybe we should question the answers. So this idea of inquiry, which is the Indian philosophical tradition, they go as bold as saying, when will you get enlightenment? When the Veda becomes Aveda. That means you kind of go beyond the printed word. You're not a prisoner of the printed word. You're not a prisoner of the dogma. So you have to go beyond traditional forms of thought in order to get understanding. That's just a good cartoon to illustrate this idea. But now I want to talk about what is the essence of this reinterpretation. It's to see familiar things in a new light. I've always defined genius as the ability to see the extraordinary in the ordinary. In fact, what's extraordinary right now is I'm sitting here somewhere in Canada, and you are sitting somewhere in India, and we are actually talking to each other. So this is an extraordinary event. I am speaking, and you are understanding. That extraordinary event. How is this possible? See, so many things of everyday life are extraordinary. And so this perception of beauty that I talked about, the aesthetic quality of acquiring beauty, part of that is the aesthetic quality of acquiring a taste for wonder. Everything around us seems to be quite wonderful. The things that are familiar in everyday life are transformed into a certain sense of wonder. So let's take a well-known theorem now in terms of mathematics. Every natural number can be written as a product of prime numbers uniquely. Well, you all know that, and I want to kind of look at it another way. Is there a reformulation of the same unique factorization theorem that leads to a higher understanding? And Euler thought in this way, and he discovered that unique factorization theorem can be written analytically. There's Euler. So on the one hand, you have all the natural numbers, and somehow you'll form a series using these natural numbers, 1 plus 1 over 2 to the s plus 1 over 3 to the s, and so on and so forth. And since every number can be written as a product of prime numbers uniquely, it can also be written as an infinite product over primes. So Euler thought this is really neat. On the one hand, you have an infinite series, but on the other hand, you have also an infinite product, and that you can connect these two. And his proof of the infinitude of primes is the divergence of the harmonic series, on the one hand, says the left-hand side, the sum, the series diverges, goes to infinity when s goes to 1. And therefore, if there were only finitely many primes, the right-hand side has to go to a finite limit, and that's not the case. So since it's not the case, there have to be infinitely many primes. So this was his proof. This reformulation opens the door to the study of prime numbers by analytic methods. So this is a big deal. Sometimes I've heard some of my colleagues, I will not mention who they are, would say, oh, what's the point of reproving something that's already known? Well, it has to do with reinterpretation. It opens the door for new ideas. So now we'll reinterpret Ramanujan's conjecture. So here Ramanujan had this tau function. And his first conjecture is, first and second conjecture actually, is the statement that these two things are equal. So the first two of Ramanujan's conjecture can be reformulated as saying the sum and the product above are equal. And the first two conjectures were proved by Mordell in 1917, but it was left to Erich Hecke, who in 1936 gave the theoretical basis for Ramanujan's discovery. So here's again an interesting thing that I would caution people trying to do research. No topic is ever finished. No topic is ever finished. And we have to learn to look at things in a kind of wonderful way. So in the case of Mordell in 1917, he proved the conjectures all right, but he never realized the significance of his own work. Sometimes we may denigrate our own work, and in that process, we may not see the significance of it. So Mordell didn't think there was any big theory there, and it was only left to Hecke, who practically 20 years later gives what is now called Hecke theory. And this, of course, is going to lead to the theory of automorphic forms and so forth. So it was a big deal. The third conjecture was also deep, very difficult. And it was solved by Pierre Deligne in 1974 using heavy-duty algebraic geometry. To this day, and we don't have a proof of this fact that does not use algebraic geometry. So the question is there one? I don't know. So this is, again, something wondrous to ponder over. But this is what I'm trying to say. These are questions might be fascinating, but it may be the opportunity or the occasion for us to discover new theories. And you have to reinterpret. Much of the solution of Deligne on the third conjecture of Ramanujan has to do with reinterpreting the tau function as counting something. It's used in a problem of counting something. A fifth method of research is what I would call analogy. Method of analogy detects similarities between two seemingly separate ideas and tries to find an underlying theme for which to look at both of them. Instance in the case of zeta function, Euler products and Ramanujan's products. So there seems to be already some similarity between the Riemann zeta function as demonstrated by Euler in his discovery of the Euler product, and Ramanujan's series, which also had an infinite product over primes. So these seem to be similar. That intuition is correct. So these two seem to be similar, the zeta function and the Ramanujan series. They both have an Euler product. This guy has an Euler, but the Euler product in the tau case is a little bit more complicated than the zeta function case. But you can see now, with these two examples in front of you, that there seem to be some patterns. The development of this analogy is actually what is called the Langlands program. A sixth method of generating questions is what is called transfer. The method of transfer is to take one idea in one field and to transport it into another field. So sometimes we find the world of numbers is similar to the world of functions. What's often called the function field version. And so questions in the realm of numbers can be asked in the realm of functions, and vice versa. Sometimes questions in the field of functions can be transferred into the field of numbers. And so this kind of symbiosis between two worlds that are not related perhaps, but are related either by analogy or some sort, can lead to transfers of method from one idea into the other. In one aspect, it is to look for applications, whether in the theoretical realm or the technological realm. So this is another interesting thing. I just finished teaching a course on cryptography last year. And for those of you who have studied cryptography, you will know that many of these encryption algorithms that are being used now really rely on very basic number theory that was discovered 300 years ago. And so the questions that the computer science people had asked is, how can I use this? How can I transfer this idea into some sort of technological realm? This is what they were doing. So the idea of applications, an example is provided by coding theory. In the 1950s, a fundamental problem was how to deal with errors in the transmission of a signal. So in the 1950s, that's the dawn of the what's called the space age. People were putting satellites into orbit. And the question is, satellites transmit back information to planet Earth through radio waves. And these radio waves are transmitted from the satellite, and then they might, travel huge distances, let's say through the asteroid belt or whatever, and they may get distorted. And so the original signal that was sent gets distorted. And when we receive it, we will not be receiving the original signal. So how to figure this, how to correct that particular code. This is what's called a theory of error corrected codes. This problem was first addressed by Claude Shannon in a fundamental paper in 1948. It's called The Mathematical Theory of Communication. Very beautiful paper, by the way. If you haven't read it, you should probably read it. It's based on very simple mathematics, and it's essentially opens the door of how to use finite fields to design what are called error correcting codes. And you may know what's most famous of these codes is what's called the Reed-Solomon codes. If the data is to be transmitted as a sequence, A0 to AM-1, with the AI lying in some field of P elements, P being a prime, then the idea of Reed and Solomon is to create a polynomial using those coordinates. And if G is a generator, we transmit f of G squared, f of G to n with n larger than m, so that now you have more input data than the degree of the polynomial. And then, as you know, if you have more values of the polynomial than the degree, then you immediately can reconstruct the degree. So this is one method. A famous theorem Lagrange tells us that polynomial of degree m can have at most m roots in the field, and therefore this simple theorem, where was Lagrange? 18th century. Where's the Reed-Solomon codes? 20th century. Simple idea from several centuries back is used in this remarkable way. So this is another mindset. You can sit in a class where you're learning high school mathematics, and you ask yourself, how can I use this in some sort of technological innovation? So this idea now, this simple idea, is now used in satellite transmission, cable television, all forms of digital media. And how in the world are you able to fit an entire library into a memory stick? So this whole business of data compression relies on the theory of finite fields. Big idea. A seventh method of generating questions is what I call the method of induction. Induction is really a method of generalization. By the way, induction is talked about not as mathematical induction, but method of generalization is talked about in the Nyaya school of Indian philosophy and many of the Vedanta schools as well, methods of getting new knowledge. The most familiar instance of this is, of course, mathematical induction. And here's an example discovered by Aryabhatta in 500 CE. He notices, hey, 1 cubed plus 2 cubed is 9. That's a perfect square. 1 cubed plus 2 cubed plus 3 cubed is 36. Hey, that's another perfect square. And so you guess that sum of the first n cubes is a perfect square, and you can actually prove this by induction. Now I want to give you a more profound, perhaps deeper example of the method of induction, and it's given by the theory of L functions. There seems to be already now a hierarchy of L functions. So you have Euler, Riemann, Ramanujan discovered special cases of a hierarchy of L functions we now know exist corresponding to GLN. GLN is the general linear group of n by n matrices over any field. You can have the entries in a field. It doesn't have to be ordinary real numbers. And this is, the idea is really what's called the Langlands program. Roots go back to Hecke and Harishchandra's work using representation theory, p-adic representations, which Harishchandra worked on. And then finally, these p-adic representations, how to paste them together into some sort of global representation, essentially what's called the theory of Euler products, a famous book written by Langlands when he got the epiphany, some form of spiritual epiphany that he had in the 1960s, when he could see that there's this hierarchy of L functions that is suggested by this, these special cases, examples of Euler, Riemann, and Ramanujan and Hecke. And he noticed that the link that you need is the work of Harishchandra on p-adic representation. So this is a big idea. So this is essentially Langlands program. Finally, I want to mention what's called the converse method of generating questions research. So whenever you have a theorem that says A implies B, the question you can always ask is, does B imply A? It's a nice way to generate meaningful questions. Often leads to profound discoveries. An example is provided by the discovery of electromagnetism. So in the 19th century, everybody knew that an electric current creates a magnetic field. And the question was, does a magnetic field create an electric current? And probably most of you know, this is what the famous discovery of Michael Faraday, and it led to the theory of electromagnetism. By the way, I don't think many of you know, maybe some of you don't, but the theory of electromagnetism, as developed by James Clerk Maxwell, is really responsible for our modern version of vector calculus. So we tend to teach vector calculus as an independent mathematical theory, which it is, of course, there's no doubt about that. But the origins of vector calculus has to do with trying to understand electromagnetism. And sometimes you may find teaching vector calculus through the lens of Maxwell or Maxwell's equations will help the student understand many of these operators, divergence, curl, gradient, vector, and all these things. So these are common things in vector calculus, but they really arose in the study of electromagnetism. So anyway, this illustrates a good way of trying to understand it. Whenever A implies B, does B imply A? It's just not an idle question, but it can lead to very profound ideas. So let me try to summarize in case you haven't been taking notes, what I just said. The first method was the survey method of generating questions. Gave the example of the periodic table. The second method is by the method of observations. Observations often lead to conjectures. And a fourth method is reinterpreting. So to see the extraordinary in the ordinary, try to see whatever you think you understand, to try to look at it in a different light. It goes back to that joke, what is 2 + 2, you know, whether it's the physicist or whether it's the engineer, whether it's a mathematician, the philosopher, the accountant, each one is seeing the world in a different light. So reinterpretation has this idea, yada bhavam tada anubhavam. You know, somehow if you have a particular feeling or attitude towards something, that determines your experience. So if you change the attitude, you can change the experience. Then the method of analogy, seeing this world looks something, it's not identical, but it looks similar to the other. And then transferring methods from one area of mathematics to another area of mathematics, from one area of science to another area of science. And then the inductive method, which is essentially generalization. So seeing special cases and finally guessing the pattern for generalization. And finally, the converse method of generating questions. So one interesting way of understanding things or remembering things is what is called the method of mnemonics. So if you haven't figured this out yet, the mnemonic for this lecture is Socratic. And if you know about Socrates, Socrates is famous for advocating the method of questioning, method of questions for research. So I hope it has inspired you. Let us churn our mind and journey inward, because when we journey inward into your own mind, you will find gems of great discoveries. Thank you for your attention.